Hello everyone, I'm Weiren, a postdoc at UC Leuven. This is work collaborating with my previous colleague Tao Yu and my previous supervisor, Professor Junlin Xiong. Here we focus on stability analysis for impulsive switched systems with constraint switches and impulses. My presentation has 4 parts, and we start with the first part, background and motivation. Impulsive systems and switched systems are 2 special classes of hybrid systems and can be used to model many physical systems, such as mechanical systems, circuit systems, multi-agent systems, and networked control systems. If both impulsive and switching phenomena exist synchronously in a dynamical system, then this system is called an impulsive switched system. Based on existing works, we can roughly categorize impulses and switches into 2 classes. The first one is deterministic class, and the second one is the stochastic class. Regarding the first class, many results have been reported. In particular, both time-dependent and state-dependent deterministic switches or impulses have been studied extensively. However, there are few works on random switches or impulses. To be specific, in existing works, most random problems are for system dynamics. In terms of random switches and impulses, only the Markovian switching case has been considered. From these discussions, an obvious problem is how to deal with the case of random switches and impulses. In this presentation, we will investigate this problem from the perspective of stability analysis. We consider nonlinear impulsive switched systems whose dynamics is presented here. X is the system state and capital I is the impulsive switching time sequence, which is assumed to be strictly increasing. Both sigma and theta are switching signal for continuous and impulsive dynamics. These 2 switching signals are assumed to be piecewise continuous and mutually independent. The function FL and HM are assumed to be locally Lipschitz and satisfy the linear growth condition. Therefore, the existence and uniqueness of the system solution are guaranteed. Before introducing constraint switches and impulses, we present a motivation example that is IEEE 802.15.4 network. Specifically, before transmitting the data packet via this network, 2 operations are implemented: back off to reduce the packet collision, clear channel assessment to evaluate the communication channel. Therefore, these 2 operations are deterministic, whereas the length of the back-off period is random and the results of the clean channel assessment are random. These results include another back-off, transmission failure by finite evaluations and packet discard, and transmission. In the transmission process, whether it is successful transmission is random. From this example, we have 2 operations. First, not all switches and impulses are arbitrary or conform certain distributions. Second, both deterministic and stochastic properties may be mixed in different periods. From previous 2 observations, we present constraint switches and impulses to be studied via this assumption. In this assumption, at each jump instant, the switching of sigma and theta are constrained related to the previous modes. The constraints are presented via capital LL and capital MM. This assumption is general enough to include many existing cases. For instance, if capital LL and capital MM have 1 element only, then it is the deterministic case. If capital LL and capital MM equal to capital L and capital M respectively, then it is the Markovian switching case. If one signal is deterministic and another is random, then it is the combination case. To study the case of constraint switches and impulsives, we next introduce the stability to be achieved. We are interested in stochastic global asymptotic stability. I would like to emphasize here that this work can be extended to address stochastic input to state stability by taking external disturbance into account. To achieve the desired stability, the technique to be applied is mode-dependent average dwell time. Since it is defined for each mode, we first define the switching number and activation time of the mode air in given interval. Then the definition of the mode-dependent average dwell time is given to constrain the switching frequency of the mode air on average. In the following, we present our main results on stability analysis. To be specific, we consider 3 cases. The first case is that all subsystems are stable, whereas the impulsive dynamics is not. To begin with, the derivative of the Numerical function is given to simplify the notation. Then we have theorem 1. If all these 4 conditions are satisfied, then the desired stability is achieved. The first condition issues that the Numerical functions are radial unbounded and positive definite. The second one shows the decrease of Numerical functions in the continuous interval, which corresponds to the case that all subsystems are stable. The third condition implies the estimate of Numerical functions at the jump instance. The final condition is the mode-dependent average dwell time condition based on the coefficients in previous 3 conditions and issues the system stability by constraining average dwell times of all subsystems. We do not show the proof in detail but the sketch. From the second and third conditions, we first estimate the Numerical functions for 2 successive discrete time instants, and then obtain the estimate of Numerical functions for any continuous interval. Using the mode-dependent average dwell time condition, we show the decrease of Numerical function along the time line. Finally, from the first condition and Markov's inequality, we conclude that the system is stable. The second case is that impulsive dynamics is stable, whereas all subsystems are not stable. Following the same mechanism as in the first case, we have theorem 2. Different from theorem 1, lambda air is positive to show the instability of all subsystems, whereas mu Lm is smaller than 1 to show the impulsive dynamics is stable. Its proof is similar to that of theorem 1. The third case is that some subsystems are stable, whereas others are not. To investigate this case, some auxiliary notations are needed. First, based on whether each subsystem is stable or not, we derive the index set into 2 parts, the stable part and the unstable part. Note that these 2 parts can be overlapping, such that some subsystems are only unstable in finite time interval. For these 2 parts, we divide their total activation times and the individual activation times for each subsystem. With these auxiliary notations, we derive theory 3, the notation C.1 for the stable part, and the condition C.2 is for the unstable part. The mode-dependent average dwell time condition is determined via the relation between the capital TUL and the capital TL. In the third case, impulsive dynamics can be either stable or unstable. The difference lies in that if the impulsive dynamics is stable, then the mode-dependent average dwell time condition is arbitrary. Otherwise, the mode-dependent average dwell time condition is constrained. Next, we present a numerical example to illustrate the derived results. Consider this impulsive switched system. The switching among 3 subsystems is deterministic, whereas the switching among 4 impulsive jumps is random. That is, the first and fourth jumps follow the third jumps. The probabilities are 0.3 and 0.7. We show 2 cases. In the first case, all subsystems are stable, and we can derive the mode-dependent average dwell time condition from theory 1. The convergence of the system trajectory is shown in this figure. In the second case, the first 2 subsystems are stable, while the third one is not stable. From theory 3, the model-dependent average dwell time condition is obtained, and we can see from this figure the guarantee of the system stability. Before ending my presentation, let me give a brief summary. In this work, we investigated impulsive switched systems with constrained switches and impulses, and derived sufficient conditions for system stability in 3 different cases. The derived result can be extended further to the time delay and robust stability cases. In addition, how to apply the derived results into practical systems like networked control systems is an interesting topic. That's all my presentation. Thank you.